In this lecture, we're going to discuss torque and magnetic dipole moments. So let's begin by recalling the relationship between electric current and magnetic fields. So anytime we have an electric current within a magnetic field, that magnetic field will create a magnetic force on that electric current. So once again, an electric current inside a magnetic field feels a magnetic force as a result of that magnetic field. So let's suppose we have the following region of space in which we have a uniform magnetic field B that points in a positive direction along our x-axis as shown by the following blue magnetic field lines. So let's suppose we take a rectangular loop of wire in which we have an electric current and place it into our magnetic field as shown. So notice our electric current begins on this end, travels through our wire, and exits at this end. So these orange arrows represent the direction of our electric current within our conducting wire. Now, let's suppose the height of these sections of the wire is given by L and the width of these sections of wire is given by X. So because we have an electric current inside a magnetic field, that basically implies these sections of wire will feel a magnetic force. So let's determine what this magnetic force is, and let's begin by examining the horizontal sections of our wire. So, notice these horizontal sections of the wire lie parallel with respect to the magnetic field. That means the angle between the magnetic field B and these sections of the wire will be 0. And because the force depends on the sine of the angle and sine of 0 is 0, that implies the magnetic force on these two horizontal sections will be 0. So these horizontal sections of wire feel no magnetic force as a result of this magnetic field. Now, let's move on to examining these vertical sections. So these sections lie at an angle of 90 degrees with respect to our magnetic field. And sine of 90 is 1, so that means these sections will in fact feel a magnetic force as a result of our magnetic field. Now, let's apply the right-hand rule number 2, to determine the direction of the forces acting on these two sections. So we take our hand and we point our fingers in the direction of our electric current. So in this section, our electric current points upward. Then we take our fingers and curl our fingers in the direction of our magnetic field. So it's this way. So we basically have this way, and then we extend our thumb in the direction of our force. So the magnetic force acting on this section of the wire will point into the page as shown by the following X. So this X means the force points into the board. Likewise, if we apply the right-hand rule onto this section of our conducting electric wire, we see the force points out of the board. So one force points into the page, the other force points out of the page. So we orient our fingers in the same direction as our electric current, so that points downward. We curl our fingers, and then we extend our thumb, and that points out of the page, so our force points in this direction. So these two forces will create a net torque. So once again, the horizontal sections of the wire, these sections, will feel no magnetic force because sine of the angle 0 is 0 and the force depends on the sine of the angle. Now, however, both vertical sections will feel a magnetic force. By the right-hand rule, the left side of our vertical section will feel a force that points into the board, while the right side will feel a force that points out of the board. These forces will add to essentially create a net torque acting on our loop of wire. Now, let's actually calculate what this net torque is. Now, recall that the magnetic force acting on either of these sections is equal to the product of the magnetic field B, our I, the current in our loop, our L, the length of these sections, and sine of the angle theta, the angle between our B and our length. So in this case, the angle is 90. Now, also recall the torque is equal to the cross product of our force and our lever arm. Now, the lever arm in this case is simply half of this value. So this is our axis of rotation, and the axis of rotation about which this loop rotates cuts the section directly in half. So our lever arm, the perpendicular distance between this section and the axis of rotation, is x divided by 2. So the net torque is equal to the sum of the torques. So we have the torque as a result of this force plus the torque as a result of the second force. And since the torques point in the same direction, they both have a positive sign. So torque 1 plus torque 2. Now torque 1 is equal to force 1 multiplied by lever arm x divided by 2, and force 2 multiplied by lever arm, so x divided by 2. So these are our two torques as a result of these two forces. Now, by this equation, force 1 is equal to B times I times L times sine of the angle 90, which is simply 1. And force 2 is B times I times L times sine of the angle theta, which is once again 90, so that gives us 1. So we combine these two results and we find that the net torque is equal to I multiplied by L multiplied by X multiplied by B. Now L multiplied by X is simply L multiplied by X, so it's the area of this loop. So we can replace the product of L and X with simply A. So we see the net torque acting on a single loop of wire, of rectangular wire within a magnetic field B, is equal to the electric current I multiplied by the area of the loop A multiplied by the magnetic field B. Now, if we stack n number of identical rectangular loops on top of one another, so we take a second loop, place it on top, a third loop, place that on top, and continue doing that n number of times, then the net torque becomes simply the sum of the torques given by this equation on each one of those loops. So we're summing them n number of times, and that is equal to n multiplied by I times A times B. This gives us the net torque acting on n loop of rectangular wires inside our magnetic field B. Now we are ready to define what the magnetic dipole moment is. The magnetic dipole moment, which is given by mu, is equal to the product of Ni and A. So this product, Nia, is known as the magnetic dipole moment. And notice, it's a vector. And the direction of this magnetic dipole moment points in the same direction as our area vector, and the area vector points in the direction perpendicular to the plane on which the loop is found on. So, because this is our magnetic dipole moment, we can essentially replace our Nia with the following result. So we see the net torque is equal to Nia cross product B, and Nia is simply mu, so mu cross product B. So because by definition of the cross product of two vectors is equal to the product of the magnitude of those two vectors and the sine of the angle theta between them, this becomes mu multiplied by B multiplied by sine of the angle theta, the angle between these two vectors. So, whenever we have an electric current, we have a rectangular loop of wire that contains an electric current that lies inside a magnetic field, it will have a certain potential energy as a result of its position within that magnetic field. That's exactly what we're going to discuss in this last section. So energy required to rotate a loop of wire inside a magnetic field B. So to rotate a loop of wire inside a magnetic field B, we must do work against that magnetic field. So against the torque that is created by that magnetic field. Now let's begin by calculating the equation for our potential energy that is stored in our electric wire as a result of our magnetic field. So recall that the potential energy U is equal to the integral of the torque and our d theta, where d theta is simply our differential angle, our change in position of the angle. So, since torque is equal to this equation, we simply replace it with this result. So N multiplied by I multiplied by A, which is simply our mu, multiplied by B, multiplied by the sine of the angle theta, where the angle theta is simply the angle between our magnetic field vector and our area vector. So these four values are constants. We can take them out of our integral, and if we integrate sine theta d theta, that gives us negative cosine theta. So our energy stored within our electric current within the wire inside the magnetic field is equal to the negative of our magnetic dipole moment mu multiplied by our magnitude of our magnetic field B multiplied by the cosine of the angle theta between these two vectors. So we see that our quantity of energy stored within our loop is equal to negative of the dot product of our magnetic field and our magnetic dipole moment. So notice we choose our potential energy inside our loop to be 0 when the angle is 90 with respect to our magnetic field.